Welcome. Let me get back to the Brouwer conjecture, probably the last time, because I already spent 3 weeks on this and I have to wrap this up. It's a very beautiful problem in graph theory, spectral graph theory, estimating the sum of the largest k eigenvalues in terms of the number of edges and k. Very strange conjecture somehow. If you look at the kind of what previously has been done since 100 years, Schur started with in general, for general matrices, self-adjoint matrices for the diagonal entries of a matrix, and then you get the lower bound and upper bound, which I worked on a couple of years ago. And then there is this Brouwer estimate. One can show the kind of related with, if you don't divide by 2 here, this estimate holds always, and that follows from a result of Brouwer and Hemmers, the guys who were, writing this, Bible on spectral graph theory. So it's a beautiful problem. I tried to use induction or use some interlacing, like for this result here. And I found this week a nice alternative. There's a little bit a simpler approach when you just do edge removal. When you do an edge removal, then the spectrum goes down. And so this also kind of ties in what I mentioned before. With Hadamard, you can actually estimate how fast this goes, how much this goes down. It goes maximally down by 2 by Hadamard. I mentioned this last time, but you can also say it cannot go more down than the next eigenvalue. So there is an interlacing going on also here. You find this in the Australian book, Gotzel and Boyle. These are 2 Australian mathematicians who wrote a nice textbook in 2001 on algebraic graph theory. You find it there. Let me just try this approach to actually say something about the Brouwer conjecture. And here's a theorem. So we have a graph which I have to assume to be large enough with respect to the maximal degree or maximal spectral radius. It's essentially kind of estimating this is also estimating the spectral radius, but I take the vertex degree because this is more catchy and it can be easy, it's easier to use. So if you take 4 times the vertex degree, the maximal vertex degree squared, and n is larger than that, for example, for large manifolds, this is the case. What also is known, and you find this in a paper of Hemmers, Mohammed Dahin, and Taifi Razal, it has been proven for trees. So, for example, if you take a star, then it's kind of explicit. You can explicitly get the eigenvalues of a star, and you take different stars and put them together, and then you can show that it's actually even stronger. The S case doesn't even grow, grows m plus something linear, not quadratic. Also, then we can use a well-known result, since graph theory has been, investigated by Cayley and others. So you can even count the number of spanning trees. So it's a subgraph, which is a tree, and covers all the vertices. So it has the same number of vertices than the graph, and of course much less edges. It's just n-1 edges. We have this result, nice result about the interlacing of the eigenvalues, and let me just see how we can use this to prove this theorem. So first of all, we just take a graph which satisfies this condition, and we take a spanning tree h0. So that's drawn here in purple, h0, then we take h1, we add an edge, h2, etc., until we reach g. So we increase that, and we will show that each increase continues to satisfy the Brouwer estimate. If the Brouwer estimate holds for HL, then it holds for HL plus 1. I call here just A HL and B HL plus 1, so that we don't have indices for these graphs. And what is nice is kind of, if you have this, all these are all subgraphs of G, so the vertex degrees are all bounded by d1g. So we have a global bound on the vertex degree. And then this is actually how I tried now for 2 weeks to prove the Brouwer conjecture, and embarrassingly actually had here forgotten the L1, the lambda 1, because I was used to think about coming from the smaller eigenvalues. If you take the lambda 1, that's the leaking eigenvalue, that's the something you have to estimate. But then with this interlacing, you can estimate the other eigenvalues. Lambda 2 is smaller than mu1, so you have the graph A, where you already have established the Brouwer conjecture, and then you increase, you add an edge, and then the eigenvalues grow. But they are interlaced nicely, and so what you can say is that the sum of the first k eigenvalues of B is lambda 1 plus then the k minus 1 largest eigenvalues of B also. So, and then this is by the interlacing here. This is smaller or equal. The lambda 1 stays the same, but the mu1 has become bigger than lambda 2, mu2 bigger than lambda 3, etc. So we have this. And now we have only k minus 1 terms. So there is a m plus k times k minus 1 half, where ma is the number of edges in A. Now, if you go from k minus 1 to k, then you add k here. So that's why we have a lambda 1 minus k. Here we take that out, and then we have the bka. Now, this is by assumption, right? K is larger than, so that's kind of the assumption, the first case assumption is k is larger than the 2 times d1, and then we have this k is bigger also than lambda 1, and then this is something which, if you take it away, makes things bigger, and then you have to estimate. So that's the estimate which I really liked, and kind of, but doesn't work because we have still the case when k is smaller than d1g. We have to kind of, also cover that situation. But then we just write down the sum of the first k eigenvalues of B, and that's smaller than k because there are k terms times the maximal eigenvalue of B, which is smaller or equal than the maximal eigenvalue of the 2d1 just by the global bound, and that's 2d1 times 2d1, which is 4d1 squared. The assumption says that n is larger than that, or larger or equal than that, and because we have something which includes a 3, then we have more than we have n plus 1. No, this is smaller or equal than n plus 1. And that's smaller or equal than bk of B. Just write this down as B. So that's the argument. I think it's quite a nice kind of result. It adds to the confidence that this Brouwer conjecture is true. I still, have not enough respect for this conjecture. I would actually think in the next 10 years one will prove it, because it doesn't look like an impossible thing to do. But who knows? Famous last word. That's it for today.